Ready to roll?
Yeah, I think so.
We have a car in the loading dock area. Once again,
We need to start filming.
Okay, everything's running.
Yeah. Okay, ready?
I'm waiting for this announcement.
Projectiles, or things flying through the air, are best described using vectors. We can split our vector into its horizontal and vertical components. If air resistance is negligible, the only force acting on our object is gravity, pulling it down. This means that the horizontal velocity doesn't change, and we can use these simple constant velocity equations to describe it. Then, we can look at the vertical motion separately with our normal kinematic equations. The vertical motion determines how long the object is in the air. So, as long as we know the initial position, the initial velocity, and the angle between the velocity and the horizontal, we can calculate everything we want to know about the object's motion.
So here's a fun real-world example of a projectile in action, an apple being launched from a giant slingshot. This modern siege weapon can be described using the properties and equations we just learned. Once the apple is in the air, it is only subject to the force of gravity, which accelerates it constantly downward, causing it to travel in a parabola directly into our target.
Hello, today we're talking vector basics. As you already know, scalar and vector quantities are different. Scalars just have magnitude, while vectors have both magnitude and direction. When drawing a vector, we first draw the tail and then the head of the vector, giving it both magnitude and direction. The second part to vector basics is vector addition. First, when drawing the two vectors, connect the first vector's head to the second vector's tail. To add them, just draw a resultant vector from the first vector's tail to the second vector's head. Have fun!
Okay, Hi, I'm going to talk about energy. Energy is the ability to do work. Energy is also a conserved quantity, meaning the total amount in an isolated system stays the same, but it may change forms, like we'll see in a second. While it also will not change quantities unless acted upon by a non-conservative force. In this case, we have a ball on the top of a hill, and it has potential energy, modeled by mgh, mass times gravity times height. And then once this ball is pushed down this hill, it's rolling and losing potential energy, and it's increasing its kinetic energy. When it's at the bottom of the hill, it is all kinetic energy and no potential energy, modeled by 1/2 mass times velocity squared. Once this ball runs into the spring, all of the kinetic energy is going to be transferred into spring potential energy by loading the spring. The mechanical energy is known as the kinetic energy plus the potential energy, and this quantity stays constant in the system. It does not change unless you have a non-conservative force, like adding a push to a ball or kicking something. So I have some examples here, in this case of a spring. When a spring is oscillating up and down, it has potential energy at the top, and then at the bottom it has kinetic energy. Indeed. And then with this ball here, when you throw it up at the top, it has potential energy, and then at the bottom it's all kinetic energy. So it's changing forms. But the amount in the system is not changing. It's just changing forms. Our projectile's energy is simple. When the slingshot is released, its spring potential energy is converted to the apple's kinetic energy. Then, some of that kinetic energy turns to gravitational potential energy as the apple rises into the air. Once it starts coming back down, the energy changes back into kinetic energy until the apple hits the ground.
Potatoes. Why'd you do that? Oh! You idiot.
Okay, here we go, Thomas. We can see a vector in action with the initial velocity of our apple here. As you can see, the vector points in the direction of the apple's motion with a magnitude equal to its speed.
Thanks for tuning in to our final AP Physics video. Hope you enjoyed it. See you next time.